Hello and a very warm welcome on behalf of NTI Audio. The topic that we have prepared for today are advanced issues of FFT analysis. Actually, this webinar is a follow-up presentation of the last webinar that we presented on the basics of FFT analysis. My name is Markus Becker and I am assisted today by Greg Schmiedli, the product manager of the FX line. He will take care of your comments, of your questions, and answer them whenever possible during the webinar. The contents that we have prepared for you start with a more in-depth look at the window functions, followed by some words about aliasing and averaging. We will furthermore introduce the difference between the maximum peak and the power results display and explain the implications of that on the calculation with FFT data. We have also prepared a practical presentation for you with some examples, and we will then summarize what we have shown to you, add some hints, and eventually come back to your questions and comment some of our answers. We expect that the whole webinar will be in the range of about half an hour. Let us first start with the window functions, an issue that we already raised in our last webinar. You remember that the FFT calculation bases on sampling a part of the input signal and then concatenating this segment furthermore so that the FFT can calculate the corresponding spectrum. However, this concatenation process sometimes causes transitions, as you can see here, and these transitions in return are the root cause of the leakage effect or the smearing effects that you see here in this spectrum. Instead of a pure single bin, which would represent the pure sine wave that we have at our input signal, the spectrum has a shape that is due to these transitions. The countermeasure against this leakage effect is the application of window functions. And actually, there are many different window functions available. I have plotted just 4 examples here on my slide. These window functions, actually, you see that here that are the shapes in the time domain. So that means that these window functions attenuate the fade in and the fade out part of our segment, of the sampled segment of our input signal. And this way, they smoothen the transitions between these segments, which results in a reduction of this leakage effect. Having said that, there are a lot of different window functions for different purposes. And it is a big issue to find the optimum window for your application. And it is not very easy to nail that down to a simple rule. I have highlighted here 2 window functions, the Han and the Blackman-Harris. These are very popular, very widespread window functions that cover almost a big majority of the typical applications, and they are also implemented in the FX100. But let me give you some more basic information, basic advice on how to select the proper window. On this slide here, we see the spectrum of 2 different window functions. And what you see is that every window function is always a trade-off between amplitude accuracy and frequency selectivity. What does that mean? If we look at the red curve, for instance, the red curve represents a specific window functions. You can see here that it damps the side lobes very strongly. So we have almost only this central lobe representing the fundamental frequency of our input signal. And the smearing effects, the leakage effects, is reduced to a very low level here in the side bands. On the other hand, you can also see that the red curve is much wider compared to the black one. So the singular frequency that stands behind the input signal comes or is less clearly visible with the red window functions compared to the black window functions. On the other hand, the black window function has the drawback that the damping of these side lobes is less strong as with the red one. So that visualizes this inherent trade-off between amplitude accuracy and frequency selectivity. There is no window available that handles both in an ideal way. It's always a compromise. Here you can see the spectra of the two window functions that I mentioned before, the Blackman-Harris in green and the hand window in red. And you can also see that the Blackman-Harris window has a better damping of the side lobes, whereas the hand window is tighter, is narrower here on that level, which means it has a higher frequency selectivity. Consequently, the hand window would be more suited to differentiate signals where you have, for instance, two sine waves very close to each other, whereas the Blackman-Harris window would be better suited to analyze upper harmonics. But that is just a rule of thumb. It depends always on the concrete application. Now let's get over to the next topic, the aliasing. Aliasing actually is an effect that causes artifacts due to the reconstruction of the sampled signal. Let me explain that in more detail. Here we have the input signal to our analyzer. So the analyzer would sample this input signal, and it gets consequently these numerical values representing these sampled values here. Now, based on this numerical data, the analyzer reconstructs numerically the original signal. And that is happening quite exactly here with this high number of samples for the sine wave. And based on this data, based on this reconstruction, the analyzer can calculate the bin, the corresponding bin of this sine wave. However, what happens when we have an input signal with a much higher frequency? The analyzer would do the same. It would sample this signal with the same sampling rate. You can see that here. Now you would assume that the reconstruction should result in a bin that looks like that, a much higher frequency compared to this sine wave with the same level. But what in reality happens is that the analyzer has a reduced number of samples compared to the frequency of this input signal. And this reduced number of samples causes that the reconstructed signal looks differently than the original one, because the analyzer is missing the amount of information it would need to reconstruct the original signal exactly. Now this red dotted curve after its reconstruction and calculation would cause this result. So this bin is an alias of this one. It's not the exact result. Actually, it's a wrong result because that would be the correct one. When does it happen? When does aliasing happen? It always happens when the frequency of the input signal is higher than half of the sampling frequency. The red block that you see here represents the bandwidth of my analyzer, and everything beyond this bandwidth, which is given by half the sampling frequency, would cause aliases in my spectrum. By the way, this half of the sampling frequency is also called the Nyquist frequency. What can we do against aliasing? Very simple. We have to apply a low-pass filter. Very important. It has to be an analog input filter, because if we would realize the filter in the digital domain, we would encounter the same fundamental problem. We could not differentiate a low signal compared to the alias of a high frequency signal. So by applying an analog input low-pass filter, we cut off all these upper signals that may occur here, and that way we avoid that aliases would pop up. The low-pass filter, by the way, would have a cutoff frequency a little bit below this Nyquist frequency due to technical reasons. Let's say some words about averaging. Averaging is a very important feature that you have to activate in many cases where the input signal shows some stochastical fluctuations, statistical components. And there are actually two different approaches to execute this averaging. The first one is what we call the normal averaging. Here the FFT would calculate results, spectra, and calculate the average blockwise by considering the corresponding spectra with equal weights. Let me show that. Here we have the first spectrum that we have measured. We have a second spectrum, a third one measured consecutively, and then we build the average, or the test instrument calculates the average of these three spectra. Then the test instrument, of course, continues to sample the FFT spectra, and it waits for the next three spectra until it calculates and shows the next average, and so on and so forth. In contrast, the other approach would be what we call the exponential averaging. Here the test instrument continuously calculates the FFT and averages them, but it weights the incoming spectra individually. What does that mean? Here we see the first spectrum that has been acquired, a second one, a third one. Now here the average has been calculated, but the weight of the last spectrum is higher than of the one before and the first one. And furthermore, as soon as I acquire another FFT spectrum, I immediately calculate the next FFT average spectrum, kicking out the very first spectrum and again considering these three spectra with individual weights, and so on and so forth. The first approach, the normal averaging, is typically used for single-shot measurements. Let's assume we have a production line where you want to verify the behavior of your devices under test against tolerance limits. In that case, you would switch them on, you would acquire FFT, some spectra, you would average them, and then compare them against a pass-fail criterion. Whereas the second approach is more popular for continuous monitoring, where you have a steady incoming signal which might change over time, or maybe you have to adjust specific parameters in that incoming signal or in the device that is generating that signal, and you want to continuously see what is the effect of my manipulation. In that case, you would rather choose the exponential averaging. The third very important topic that you have to keep in mind is the display, the way how you display your results. Normally, you would not show all the individual results of a FFT. Let's assume, for instance, you have a block length of 8K, which means the FFT calculation provides approximately 8,000 points. And that is definitely too much to show on a monitor or to get some reasonable result out of that. So what you do, you combine these results, all 100 results, for instance, into one block, and you show that as a bin. And that is what you see here. This is the spectrum, a very simplified spectrum of an input signal where all these underlying FFT data have been combined into blocks that is represented here. Now the question is, how do you represent these blocks if the number of bars, as shown here, is smaller than the number of bins? There are two approaches. The first one is what we call the maximum peak. So when we look at the corresponding section of our FFT signal, here the red curve behind is the high resolution FFT data. So we cut out this segment and we take a look, what is the maximum bin in this segment? And this level of this bin is shown here by this block. This block represents this part of the FFT result. The other approach is the power. Here we calculate the accumulated energy within that corresponding segment and show it here in our display. The maximum peak approach is typically used to display the curves, to watch it, whereas the power approach is essential to be used if you execute calculations. There are some calculations where you use the maximum peak, but in most calculations, as you're going to see in a minute, we would use the power approach. But keep always in mind these two different ways of visualizing or acquiring the FFT data if the number of bars is smaller than the number of bins of the FFT calculation. Now let's take a look at 3 examples of calculating FFT data. The first example, we have a spectrum and we want to know the overall level here in this orange highlighted band. How can we achieve that? It's quite simple. We take the sum of all the bin levels within that band and we sum them up with this formula. So we have to take these bin levels expressed in volt. We have to square each of them, add them up, and in the end get the square root of the sum. And that gives us the band level of this corresponding section here. Another example would be when we want to take a look at the harmonics, the upper harmonics of a signal. We see here a spectrum of a signal, here the fundamental and the first, second, third, and so on, harmonic, or this is called K2, K3, K4, K5, K6, K7, and let's assume we want to know the sum of K3, 5, and 7 altogether. Well, the approach is the same as before. We have to add the squares expressed in volt of the corresponding levels of these 3 harmonics and calculate the square root of the sum. That gives us the overall voltage of these 3 harmonics together. And the third example would be a signal to noise ratio calculation. So here we have a signal with a fundamental frequency and we have some noise to the left and to the right. And we want to know the ratio between the signal level and the noise level. How do we get that? Again, same approach. This time we build the sum of these bins to the left and to the right with the same formula. By the way, this is the RSS calculation. RSS stands for root sum square, the square root from the sum of the squared bins. And this time we use this formula together with a fraction. So we divide the level of the fundamental signal by this RSS value of the noise. And that gives us the signal to noise ratio in linear unit. We can translate that into decibel by applying a logarithm to that overall result. Now we are at the point of our practical presentation. For that purpose, I have here an FX100 on my desk, which is connected to our device under test, and it is controlled by the FX control software, which comes along with every test instrument, with every FX100. Now let us start first with the window functions. And I have here a sine wave with 1 kHz frequency without windowing. Let us take a look at this spectrum. It would look like that. And this is a typical smearing or leakage effect that you see here. The 1 kHz, you would expect a nice pure singular bin here, but in fact, due to this leakage effect, you have this smeared spectrum in reality. Well, as soon as I apply a window, in this case a Blackman-Harris, and I repeat the measurement, you see immediately the effect. The fundamental frequency stands out very clear. The sidebands are damped pretty nicely, so here you have a much clearer picture of the incoming signal. I can do the same with the hand window. And again, you see the effect. Here we have a tighter, a more narrow frequency selectivity of that fundamental frequency. However, the damping of the side bands of the side lobes is less strict, is less strong compared to the Blackman-Harris. And that gives you hopefully an understanding why the hand window, for instance, is better if we have to if we have to focus on the frequency selectivity, on the frequency accuracy of our measurement, whereas the Blackman-Harris is superior when it comes to damping the sidebands side of the fundamental frequency or of the harmonics, whatever. The next example I want to show you is the effect of averaging. And for that purpose, I'm going to switch on my continuous mode with the device under test in between. And I hope you can see that the webinar software, unfortunately, is not as fast as our test instrument here, but you can see there are lots of stochastic components, fluctuations. It's a very nervous signal, and it would be very hard for you to decide, is there any systematic issue, any systematic component in that signal, or is it just noise? But as soon as we activate the averaging, very quickly we get a nice picture, and we see here at 200 Hertz apparently there is a constant component, could be for instance third harmonic of 50 Hertz hum or whatever, but by applying the average the picture becomes much clearer and allows you to analyze the root characteristic, the core characteristic of your input signal. Just for comparison, I will activate now the normal average, the normal averaging, the blockwise averaging, and you will see the effect. Instead of a continuous update, you see now kind of a static view, and then it will be updated every 1 or 2 seconds as soon as this countdown counter that you see up here has come down from 32 cycles to 0. So every 32 cycles of the internal acquisition will be shown, will be updated on the display. This averaging is also essential when it goes into state analysis. That's what I'm going to show you here. This is just another view of my input signal, and down here I am comparing this input signal against past failed limit. So this red band that you see in the background is my past failed criterion. And if I would switch off the averaging, you can see the effect. We have lots of failed, but actually the device under test is working fine. It's just these statistical fluctuations that are causing these peaks which are exceeding the given limits. As soon as I activate the averaging, this effect disappears and I get a clear and stable past result. If I would manipulate now my device under test here, you see I'm now increasing that hum or whatever it is. You see immediately as soon as it exceeds the limits, it will give me a clear failed. A short side note, how did I establish this tolerance band? It's very simple. I acquired the average of my fundamental signal when it was good. That is what you see here. This is my golden sample. And then I added an offset and I withdrew an offset from this golden sample. And these red and the blue curve are now giving me the upper and the lower limit of my acceptance band. I also want to show you another effect here on this screen, and that is the difference between the maximum peak and the power display. You see here I have chosen the maximum peak, and what happens when I switch over to power? You see the picture changes immediately, because here now I am calculating the cumulated energy per point in my display. You may notice here I have a 16K FFT, so that means the fundamental calculation includes 16,000 results, but I'm only displaying 500. It wouldn't make sense to display 16,000. You wouldn't get any more information. But by choosing this display mode, you get some more information about the distribution of the energy and the peak level that are happening in my input signal. Well, let me show you a third project that I have prepared, and that is about signal to noise ratio measurement. I execute a single shot here. Well, in this screen here, in this window, you see the result of my measurement. You see we have a fundamental frequency here at 1000 Hertz. We have some harmonics, we have some noise below. Well, to calculate now the signal to noise ratio, we have to split this picture into 3 parts. You see here the left part, the noise, and to the left side, we have the peak itself in the middle, and we have all the noise and the rest here to the right-hand side. And we can now calculate the corresponding RSS values, the sums of these bins in these bands, and then calculate the overall result. Just to give you an idea how this happens, if I show here the properties of this graph, for instance, you see this has the input. As the input, we have the measurement result, and then we reduce the bandwidth from 20 Hertz to 950 Hertz. So this gives us the result, the numerical result. This gives us this curve here to the left-hand side. And the next step now is to calculate the RSS of that part. And for that purpose, we take the input, the graph here, and we calculate, you see here, RSS of these corresponding values. So all these calculations are already done by the FX100. It's very comfortable. And here in the overall result, you would see we do the same for the center frequency, the fundamental for the left side, for the right side, and then we just calculate the overall sum according as I showed you before. And that gives us this overall result. Well, let me get back to my presentation and summarize the content of my webinar. We started with the window functions, and just to repeat, the hint that I can give you, if you have several window functions available, toggle between them to get a more thorough picture, to get a better understanding of your input signal. Generally, the Blackman-Harris and the Han are very widespread, very popular windows. The Blackman-Harris is better when it comes to side lobe damping, whereas the Han window has a higher frequency selectivity. Talking about aliasing, the best thing that you can do is to make sure that your test instrument has a good analog anti-aliasing filter. If not, you are always encountering the risk that some parts in your spectrum might be aliasing effects, and that is of course bad because it falsifies the result. Talking about averaging, you can play around with the available parameters to get the optimum result for your application. And when it goes into calculations, it's very important to use the correct result data format, the power or the maximum peak for your calculation. Well, I'm at the end of the presentation. Thanks a lot for your attention. Bye-bye.